Okay, so this is stress X, right? And this is our stress Y. Okay, normal stress X, normal stress Y. So normal stress is anything that is perpendicular to the surface. Okay. And then could you remember our shear? So this is our shear, right? So the plane intersecting is the X plane, Y axis, the force is acting. So this is shear Y X. Okay, so today we learn about the normal stress, which is the easier one. Okay, the shearing stress was a harder one. But you guys understand the hard part, easy part is easy now. Okay, so we are calculating stresses in the X direction. So what does this actually mean, stresses in the X direction? Okay, so let's say now the simply supported beam has a cross-sectional area, and the cross-sectional area look like this. It's a rectangular cross-sectional area. Okay, so when we draw this cross-sectional area, the transformation change. So now this is our Y, okay, and this is our Z, and then this is the rotation about X now. Okay, so this is the cross-sectional view. So if I were to expand our cross-sectional view now, okay, so this is our cross-sectional view, right? So this is our cross-sectional view. And over here, I'm going to label the top as our point alpha. The bottom is our point beta. So where this is now, so over here, this is our point alpha. And over here, this is our point beta. Okay. And we know based on the bending now, or based on how the force is applied, right? So we have bending in this direction now. Okay. So this is compression. This is tension. So now we are aware, right, that this is the top is compression, bottom is tension. Okay. So the next thing that we're going to draw is we're going to sketch the distribution, the stress distribution okay, in the X direction. Stress X direction. Okay. So we are aware that the line down here, right? The line down here, this is our centroid. Yeah. So this is our centroid. Oi. So the line down there, that is our centroid. Okay. So I'm going to draw an axis now. This axis over here, right, is our stress X. Okay. And then I'm going to draw another vertical axis. Okay. So this vertical axis is our point, is our Y. Okay. So over here, basically, this is where our alpha point is, right? Over here, this is where our point beta is. Okay. So this line represents the material. Okay. I like to call this line represents the material. or the structure. Okay. So we are aware if the center is 0, okay, anything that is this side is what we call tensile or tension. What is on the other side, we are aware is called compression. Okay, we know that. So now if I were to sketch the stress distribution, right? So we know that at point alpha is under compression, at point beta is under tension. So the graph will look like this. Okay, the graph will look like this now. Okay, so this is how our graph will look like. Okay, and if we plot the axis out over here, this is our minus stress x, right? And then over here, this is our positive stress y. No, yeah, stress x, Eugene, come on. Okay. So now, regarding tension and compression, now all of you know, okay, based on axial loading, right? When tensile is pulling away from the material, or tension is pulling away from the material. When it's compression, it is squeezing towards the material. Okay, we know that. So to sketch the profile, okay, so on top, right, as I say, the structure is at the center, okay, the structure is at the center. So compression means it's pushing towards. So I'm going to draw how the stress is acting, okay. So the stresses is pressing, it's compression, pressing on the what? On the structure is pressing. And then on the other side, it is what? It is tension is pulling away, okay, from the structure. So this is how you sketch the stress distribution. Different books will have different notation, okay, but I'm trying to relate this to tension and compression under axial loading, because axial loading, this is also our stress x. When we calculate axial loading, this is also our stress x. Okay, so this is how I like you all to sketch the stress profile. Okay, now an interesting thing to see is at this point down here, when y is equal to 0, right? Our stress x is equal to 0. Okay, so this means that at point y equal to 0, the normal stress in the x direction is equal to 0, and this axis is known as neutral axis. Okay, so at the neutral axis, okay, stress in the normal direction is equal to what? 0. Okay, and the next thing I like you all to take note is this. Okay, next thing I want you all to take note is this. Okay, for this type of loading, okay, I'll write down here under centric loading. Okay, when I say centric loading, is where stress x is equal to m y over I. Okay, okay, when under centric, later on we look at eccentric. Okay, the opposite is eccentric. So this is centric, the opposite, okay, the opposite is called eccentric. Not crazy, okay. Okay, so under centric loading, okay, stress X equal to my over I, the centroid and neutral axis are at the same position. At the same position. Okay, same position, and this is only true for centric loading. Okay, so if you look over here, what do I mean by that? At the same position. Okay, so if you look at the green line that I've drawn, this is the centroid. The centroid is also on this axis over here, right? So over this point is also our what? Neutral axis, where stress X is also equal to 0. Okay, now the neutral axis is based on stress field. The centroid is based on geometry. So this is based on geometry. Okay, this is based on geometry. And this over here is based on stress field. Two very different things. Okay, one is geometry dependent or determined. One is stress field determined. Okay, any questions so far? Anyone? Okay, I don't see anyone putting up their hand, or I don't see anyone. Okay, right. So we'll go for the next one. Okay, now this page is really important. All the basic theory about bending is all here. Okay, this is very important. You have to understand this concept. Okay, because later on when it's sandwich material, eccentric loading, loading, unsymmetrical loading, we are always going to apply this theory. Okay, right. The next thing I want to highlight is this. Okay, and I think it's an important feature that you as engineers have to know. Okay, I want to highlight the similar characteristic. Okay, similar characteristic between simply supported and cantilever beam. Okay, I want to highlight the similarities. Okay, so there are two things that over here that I highlight that I want you to learn. What is the similarities, okay, between simply supported and also between cantilever beam. Okay, so I believe sometimes you have seen this before, is why we only need to analyze half the structure. Yes or no? Right? Why we don't need to analyze the entire structure? Why if the loading is simply supported, how come we can just take half of it? Right? Under symmetrical loading. Sorry, under when the load is at the center. Okay. So let's look at simply supported load or simply supported beam. Okay. Simply supported beam. So now again now this only work in this condition. Okay, in this condition. It will not work in any other condition. But this condition of loading is very common. Okay. So you have point A you have point B. And then we have the load exactly on the center. Okay, and this is our